Chapter F, the chain rule. Now for the chain rule, we're going to be applying our basic definition of a slope for the slope function or derivative. Let's write that out again, which we have seen. And that's going to be the limit of delta x going to 0 of delta f over delta x. And that's going to be the limit of delta x going to 0 of f of x plus delta x minus f of x over delta x, our formula. So now we're interested in doing a case where f is equal to a function of u, where u is a function of x. And I want the derivative of f with respect to x. Like, how do I do this? Well, what is here delta f? Well, delta f would be equal to f of u plus delta u minus f of u. That's what you would have there. And what is delta u? Well, delta u would be u of x plus delta x minus u of x. Now, since we want a delta f over delta x like this, and then we'll take the limit, we might consider doing delta f over delta u and then delta u over delta x. And see, this would suggest that if we did the limit there, that we'd have a df du and a du dx. So let's go ahead and state that here. In other words, df dx, like this, would be equal to, let's say, the limit as delta x goes to 0 of delta f over delta x, and that's going to be equal to the limit as delta x goes to 0 of delta f over delta u, delta x. Now the problem here is when delta x goes to 0, how can we be certain that delta u will not be 0? Well, let's say, suppose that delta u is not equal to 0 before delta x goes to 0. Now, if that's the case, then we're finished. We would have df dx is equal to, well, let me just emphasize that we're using the rules that if you have the limit of a sum, it's equal to the sum of the limits. And here, if you have a limit of the product, we can replace that with the limit of each component times each other. All right, now I'll list these later in our course, but we don't prove them here. That's why taking a calculus course is always very, very good to do and is required for majoring in physical science. So if we do that, we would then write the limit delta x goes to 0. I would have delta f over delta u, and I would have the limit as delta x goes to 0. You might wonder why I put the delta x there. Well, I'll fix that in a second. Delta u over delta x. And then here, as delta x goes to 0, delta u will be going to 0, so then I can replace this with the limit of delta u going to 0, delta f, delta u, and then here is the limit delta x goes to 0 of delta u, delta x. And then the limit of the individual components, we would multiply them together, we would have df du and then du dx. Now you'll find this derivation on the internet like this, and it's not really complete because we're supposing that delta u isn't going to 0 or equal to 0 before delta x slides to 0. So it's not really complete, and really shouldn't be pushing that off as a derivation. See, let's give an example. Suppose I want the derivative where I have a function that's really a crazy function. Say here's y and x, f of x here. And say I have a function that does something like this, it's doing this kind of stuff. And then, here it's going like a lot of ripples. And then it starts, doing that. So suppose I'm interested at taking the derivative at this point x. That's where I want to take my derivative, right? Now, a function that actually does weird stuff like that is, and really I would like this to be the function u, so I'm going to emphasize this is u of x here. I actually give you a function that does something like this in the book. But the point here is that we have a problem because as delta x, say you have some x here plus delta x. As delta x is going to 0, we're sliding this way to x equal to 0. The changes in the u could be 0. And you can think of that by saying, if I blow this section up, say I blow that section up and I have something like this, by blowing this section up. So I just make a magnifying glass on this section here, come over to here. The slope of u is 0 whenever it's flat. There's no slope. Well, that means delta u is 0 a lot of times as I slide here delta x going to 0. Because you can think of this as the delta x, this region in here. And as that goes to 0, we're being in big trouble. So we have to have another approach. Now, I'm going to draw a picture here. It's going to help us get out of this mess. So we have the u-axis up here. And we have over on this side the x-axis, like that. And suppose I have a function that does something like this. Goes up like this and does that. And I'm interested in the slope at this point x. Well, the actual slope itself is the tangent here. So if I did that, and I go up like this, this is the actual slope that we're interested in. But suppose my delta x goes way out here. So this is x plus delta x. If that's the case, then I would go from, say I would have a dotted line going up like this. I would be going from here up to there. And see, that's not really the slope. And well, if I get delta x going to 0, then yeah, the green line's going to blend, it's going to become the red line. I'm going to be in good shape. So for this actual slope, I'm going to go ahead and put some more lines in here like this. We got this, and we'll draw a line, say here, like that. And if we look at this height here would be u of x. Because if I put in x into the u function, I get this altitude. So this is u of x, or simply u. Now, if we look at the angle here, and we'll call that angle theta, then the actual slope is the tangent of theta. I'm going to emphasize here this is delta x. So the tangent of theta, so u prime, which is du dx, is the tangent of theta. Go ahead and draw another line out here. Now, if we go from here way up to the top, that's going to be delta u. And then I'll be interested in taking the limit as delta x goes to 0. But when it does go to 0, I get the correct slope. This slope here is a little bit in error. So for the error, what I'm going to do is say there's some epsilon error term here times delta x. So I have u of x, I have the epsilon delta x. Now what about this? What's going on there? Well, the tangent of theta would be this thing divided by delta x. But the tangent of theta is also equal to u prime. So for a second, I'm just going to let this thing be z. So if I take, say, a delta z. So if I take delta z over delta x, I have the actual slope. So this is delta z over delta x. That is the actual slope. So that means delta z is the tangent of theta, which is u prime. In other words, let's go ahead and write this out. U prime is delta z over delta x. So delta z is u prime delta x. So this here is u prime delta x. So I have a lot of stuff in this diagram. So now we remind ourselves that f is equal to f of u, and u is u of x. So now I'm going to write down here this delta u as a sum of these two terms, u prime delta x plus epsilon delta x. So in other words, delta u is u prime plus epsilon times delta x. Now I can draw a similar diagram where I have a f and a u. Then this would be delta f would be f prime, where the f prime now refers to with the u argument. Just like here, the u prime is working with the derivative of the x argument. And then I'll call this epsilon 1, and then this would be a delta u by analogy. And then I would still have one for here. I'd have delta u is a u prime of an x, and I'll make this epsilon 2 just to have two different ones in delta x. So now that I have these set up based on two of these diagrams, I only drew one. I would do one for the u and the x, but there'd be one for the f and the u. Then if I want delta f over delta x, well, what would that be? I would have here f prime of u plus epsilon 1. And then I would have I would have then for the delta u, I would have this thing. And then the delta x's here would cancel off. And now that they cancel out, when I take the limit of delta x goes to 0, error terms are going away because I'm going to blend in and have the right answers. So in other words, well, we have df dx as the limit as delta x goes to 0, then these error terms are going to drop out. See, I don't have to worry about dividing by a delta u here. In fact, I don't even have to worry about dividing by a delta x at this point. So that's going to get me, when this happens, the epsilons are going to go to 0. And when the epsilons go to 0, I'm going to have f prime of u and u prime of x, and the f prime of u is df du, and the u prime of x is du dx, and that is the chain rule. That's what we had up here with a argument that was incomplete. But then with this figure, we're all set. So occasionally, I like to be more precise like the mathematicians when subtle things like this happen. But I won't go overboard. For example, the limit of a sum is equal to the limit of each individual component. I'm not going to prove that. That's somewhat, for a physicist, like easy to understand. Somewhat, let's say, intuitively understandable. But something like this is not intuitively understandable. There's subtleties going on here with these ripples, oscillations. These are called oscillations, by the way, when that happens. There's a nice way to think of the chain rule with gears. So let's look at this little gear. This little gear situation here, this gear, which is called Y, has 1, 2, 3, 4, 5, 6 little gears. Now this U has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that means when this goes around once, the change to the Y is going to be like 3, because to keep up with it, it's got to like rotate 3 times. So here the change in Y with respect to U is going to get us 3. In other words, the Y is going to change. It's going to go around 3 times when the U goes around once. Now, if you come up here, if you count these, and you can in my book, you're going to find that here, well, there's 18 gears here, but there's 36 gears here. So when this one goes around once, this one's going to go around twice. So that means the change in U with respect to the change in X is going to be 2. So then you ask the question, what about when, say, you look at the change in Y, this one way down here, this little one, when X goes around once? Well, when X goes around once, you see the U is going to go around twice, and this is going to go around 3 times for every times that U goes around. So you're going to get the product of these two. So in other words, dy dx, which is 6, is going to be thought of as dy du, which is 3, times du dx, which is 2. So we have 3 times 2, and that gets us to 6. So it's a nice little gear analogy in helping us understand more about the chain rule. I will see you next class.